All right, so we're going to do a problem from chapter 10. The first problem we want to do is problem 10. Starting from rest, a disk rotates about its central axis with constant angular acceleration. In 5 seconds, it rotates 25 radians. During that time, what are the magnitude of the angular acceleration, the average angular velocity, and what is the instantaneous angular velocity of the disk at the end of 5 seconds? With the angular acceleration unchanged, through what additional angle will the disk turn during the next 5 seconds? All right, so you can see that, as we mentioned, there's a one-to-one correspondence when you're dealing with the rotation as opposed to when you're dealing with the translational motion. So your theta here is equivalent to your position, and your alpha is equivalent to your acceleration, A, and omega is equivalent to V. And time, of course, does not change. So it says that it starts from rest. It means that initial velocity, I forgot to put it down here, initial angular velocity is 0. So now you have the time, you have the angle, and then you have the initial velocity. Then it becomes very easy to find your angular acceleration because you have the equation that says the final angular position is equal to initial angular position plus initial angular velocity times time plus 1/2 alpha t squared. So you can see that we have all the information we need except the angular acceleration, which you asked to find. So let's do that. So you have angular position initially set this to 0. There's no angular velocity initially, and then you have 1/2 alpha, and then your time is 5 seconds, and your theta here is 25 radians. Okay, so after you do that, so you can see that your alpha is 2, and then radians per second squared. So that's your alpha. Okay, and then you'll also find the average angular velocity. So what is your AVG? So your AVG is equal to, by definition, that's just the changing angular position over the time interval. So you have this angular displacement will be just the final position, which is 25, minus initial position, which is 0. So you just have 25, and the time is 5. So you have the average angular velocity, which is 5, and the unit is radians per second. Okay. And then you'll also find what is that angular velocity at the time 5 seconds. And so another equation that relates the initial velocity to final velocity is this. The final angular velocity is equal to initial angular velocity plus the acceleration times time. You have everything in front of you. So you have the alpha is 2 and your time is 5. So you got 10 radians per second. So you can see that this is your instantaneous angular velocity at time that's 5 seconds. And then you ask, what is the new displacement after 5? Let's see, what is your ask to find? What is the additional angle will the disk turn during the next 5 seconds? So here's what I would do. Okay, if we look back to this equation, it says that what is the additional distance to travel. So you can use you can still take the initial, that is time equals to 0, and then the omega initial velocity is still 0, and then the total travel time is 10 seconds, and then you can just plug into this equation. So your theta after at time t equals to 10 is equal to initially no displacement, no initial velocity, but then time is 10 seconds now, and then plus 1/2, and your alpha is 2. It does not change, and your time is 10 squared. So what you have here is that this is 0. So what you have here is 100 radians. This is when starting from rest, and then just keep moving, like you just counting how many radians until time reaches 10 seconds. So this is 100 radians after 10 seconds. So what is the additional distance that it will rotate within the next 5 seconds? We know that within 5 seconds, this disk is going to have rotated 25 radians. So the additional, so let me see, theta, the additional would just be 100 minus 25. So that gives you 75 radians. Okay. The other way is that what you can do is if you take this theta now, 25 to be the initial, if you take this as your initial, and then your initial velocity, that will be the whatever velocity we calculated, at time equal to 5 seconds, which is 10 radians per second. And then your time, the additional 5 seconds, so that's 5. You can see that, and then you are going to use the same equation as this one, but then because you kind of like reset your clock, so your time start at 5 seconds, not start from 0 second. So what you have here is that theta is equal to theta 0 plus omega and then plus 1/2 alpha t squared. So you have your 25 and then plus omega and then times 5 and then plus 1/2 times 2 times 5 squared. So you can see that this gives you 100. So this is the final position. The final position after the additional 5 seconds. So the additional distance. So the additional distance, of course, is theta minus theta 0, which is the displacement. So you still get 75 radians. Okay. So this is just a different approach depending on when you at which moment that you take it to be the initial point. So when you use this, I still keep the initial point as the as when t equals to 0 and when there's no initial velocity. But then when you use in this equation, when you use this set of numbers, then it means that you'll actually reset your clock and then take the when the time equal to 5, the additional 5 seconds, what will be the additional 5 seconds that it traveled? So during that time, the velocity, the disk has acquired the angular velocity, which is 10 radians per second, and has rotated 25 radians. So when you can still use this equation, just that the numbers just have to be adjusted accordingly. Okay. All right. So that's problem 10, and the next we want to do is problem 35. Okay, so problem 35, what is that? Let's see. Let me draw a diagram first, and then I'll read out. Cylinder, central axis, bigger cylinder. This is a rotation axis. All right, so, and let me see. Mass is 1.25, frequency, velocity R1, R2. Okay, and this is your I1, and this is your I2. All right, problem 35, let's see. Two uniform solid cylinders. So these are solid cylinders, each rotating about its central axis at 335 radians per second. So this is the angular velocity, which is 235. And so it's rotating about its central axis. So this is the central rotation axis. Okay. Now we know that rotation inertia will depending on would change. Will be different depending on which axis that the object is rotating about. So for this one, it's rotating about the axis through the center, okay, longitudinally, and so they have the same mass, which is 1.25 kilogram, but they differ in radius, okay. And what is the rotational kinetic energy of the smaller cylinder and the larger cylinder when the radii are given? So you're asked to find the kinetic energy. So when you have an object that undergoing the pure rotational motion, it has rotational energy, and the expression for rotational energy is this. So let's say this is your 1 for this smaller cylinder. So you have 1/2, and then the expression will be instead of mv squared, it is 1/2 I omega squared. So you have your I, you have your omega squared. Now the omega, because they are rotating about at the same rate, so omega stays the same, but the rotational inertia will be different because the radius is different. Okay, so in order to calculate this, we need to find out what is I1. So when you have an object, when you have a cylinder that's rotating about its its longitudinal central axis, the expression for I is this. That's just 1/2 mass of the object and then times r squared. Okay, so then you have your K1, that the kinetic energy for object 1, that's 1/2, and then times, let me see, do I have 1/2? So this, when you plug in a number, so you have 1/2 times 1.25, and times your R is 0.25 square root. So your I1, you should have your I1, that's 0.039, and the unit is kilogram times meters. So this is your 0.039. So this is 1/2 I and then omega, and your omega is 235, and then remember to square it. So the kinetic energy for this object, you will have 1078.6 joules. So this is the amount of energy when this smaller object is rotating at that rate. It's about 1,000 joules. Now let's look at what is the kinetic energy involved when you have a larger cylinder which has a larger radius. So everything stays the same. Your K2 is equal to 1/2 I2 omega squared. So how I2, you still use the same formula. So you have 1/2 mR2 squared. So 1/2 and then 1.25, and your R2 is 0.75. That thing squared. So your I2 should have a magnitude that is 0.351, which means that it has a larger rotational inertia compared to this one. It's almost like 10 times larger, okay? And then you plug into this equation. So you have 1/2, and then I2, which is 0.351, and then times omega, and your omega is 235, you square it. So after you plug in this number, you'll find that the kinetic energy involved in order to have this heavier object, in order to have this same object, not the same object, but the same mass of object, but with a larger radius to rotate at the same speed, you would need this amount of energy to do that. Okay. So the amount of energy has to be supplied to the, to this in order for it to rotate. And what we found is that even though they have the same mass, but this one has a larger diameter, and with a larger diameter, it means that it has a larger rotational inertia. So the amount of energy involved in the motion will be larger as well. Okay, so that's basically what this problem is trying to illustrate. All right, so the next one is problem 37. All right, so again, I'm going to draw the diagram before we discuss the problem. So give me a stick. And point to mark. All right, so problem 37. You are asked to calculate the rotational inertia of a meter stick with a mass that's given 0.56 kilogram about an axis perpendicular to the stick. About an axis perpendicular to the stick and located at 20 centimeter mark. Okay, so in other words, you have a meter stick, and it is rotating, through the center because it's a uniform stick. So the central mass is right at the center at 0.5 mark, and then it's going to regulate. It will rotate about its central axis. But now, if you're asked to find the new rotation inertia when the rotation axis is not about the central mass, it's actually a little bit off. So it's like like 30 centimeters away from the central axis, and you asked to find what that rotation inertia is. Okay, and in the problem it says that you want to treat this as a thin rod. So there's a formula to calculate the rotation inertia for a thin rod. So let me just write it down. So the rotational inertia when is rotating about the center of mass is for thin rod is 1/12 mass of the object and then length of the object. Okay, so this is a rotational inertia when if you have this meter stick rotating about this axis. But then now the rotational axis is not on this at this point. It's actually at 20 centimeters mark. So how do we account for the new? So this is your ICOM. What is our new I? And you ask to find. Okay. So in that case, you will have to first find out what is the rotational inertia for through the center of mass, and then use the parallel axis theorem to find out what is the the thing that has to be modified to the ICOM in order to get your new I. So in other words, let's calculate this first. So you have 1/12, and the mass is 0.56, and then you have your L, and the L is the total length of the stick, which is 1. Okay, so you calculate this to be 0.046 kilograms times meter square. And then, how do we account for the modification to the ICOM so that you get your new rotational inertia when the rotating axis at some point away from the center of mass? So using parallel axis theorem, the new I is equal to the rotational inertia through the center of mass, and then plus the mass of the object, and then times the vertical separation between them. This is the axis through the center of mass. This is the new axis. The vertical separation between them is this. This is located at 0.5 mark. 0.5 meters, and this is located at 0.2 meters. So the separation between them is just 0.3. Okay, so you should have. So this is. Let me just write down. So let me call that h. Okay, so you have your m and then h squared. Okay, so now you have ICOM is 0.046, and then plus the mass is 0.56. And then times your h. Your h is 0.5 minus 0.2. That's the vertical separation between the two axes. And then the difference, you square it. Okay? So after you plug in the numbers and calculate this, you get your new rotational inertia, which is 0.09706 kilogram times meters. What does that tell you? This one, when it is rotating through the center of mass, the rotational inertia is actually less than when it is rotating through any axis of the that's not on the center of mass. Which means that when you rotate this stick, when you're rotating about this axis, it's much easier than when you rotate this whole thing through this axis, because the rotational inertia here is larger than the rotational inertia over here. Okay, so that's that.